all the PowerPoint stuff works, doesn't work, disappears, appears.
Well, we're live.
Yeah, we are.
Greetings, fellow nerds. Welcome to another helping of Between Two Nerds Awesome Sauce, where we talk with prominent guests about all aspects of the networking industry, from protocols old and new to industry trends and drivers to up and coming technologies, and as always, things you should know to further your career. And when I say prominent guests, they don't get much more prominenter than today's guest. Tony Lee, thanks for joining us again. How are you guys doing?
Just great. Thank you very much, Jeff.
Hey, Jeff. Hey, Tony. Hey, guys. Again, great to be here. Great to see Tony, who is by now our guest. You know, I would call you permanent guest.
Eminent guest. There you go. Preeminent. Better than saying prominenter. I just invented a word there. So, Jeff, you want to do an introduction to our topic for today?
Yeah. So very few people need introduction for Tony. Tony is the person who pretty much built most of routing as we know it today. Built it in the right way, so it works because of a lot of things he did. So, thank you for being the show and welcome. So the topic of today's show is actually I'll give it to Tony.
There you go.
Thank you, guys. So today's topic is talking about how to do a routing architecture for satellite networks. And let me go ahead and bring up slides here. All right.
And just to interject, for those of you listening, if you do a search on exactly that title, you'll find Tony's internet draft on the IETF website that'll give you some written details on this.
The draft is progress in routing working group, and Tony is going to present in Brisbane in 2 weeks.
Yeah.
And this is the name of the draft right here, so feel free to Google that. All right. So let's see. This is very much a work in progress, not complete, and so please pardon any rough edges. This is very much an engineering talk. If you're looking for fancy artwork, sorry, no. I'm very much a routing guy. I'm learning about satellites. If I get the satellite stuff wrong, please tell me, but please be gentle. I don't know too much about this, still learning. There are many ways to solve this problem. Many folks have gone off and proposed lots of things. I just wanted to see what we could do with existing technology to make this work. Satellite operators have not given us a lot of feedback on this, so there's a lot of things that could very well be wrong. And this is very much a discussion, so please feel free to interrupt and ask questions. So here's the basic problem that we're trying to work on. We've got the internet, we've got a local gateway, and it's talking up to a bunch of satellites. And when we had just geosynchronous satellites, this was a pretty straightforward problem, but it has some problems with delay and cost. And with modern technology, people were proposing doing things with lots of low Earth orbit satellites. And in particular, they're talking about tossing up lots of these satellites. The number 40,000 has been bandied about. That's probably optimistic, but at the same time, we want to architect for kind of operating at that kind of scale. And that's where we get the interesting problem. Now, one of the nice things about low Earth orbit is that the latencies come way down because it's not very high, and speed of light being fixed, being close is good. The downside of being in low Earth orbit is that you're not overhead for any length of time. I've heard the number 15 seconds for any given satellite. And so there's a lot of change. A user terminal, a user station is only going to be able to see some number of satellites, and it's going to have to shift every 15 seconds. So we've got a lot of churn going on we have to think about. One other nice thing in current technology is that people are proposing using inter-satellite links between the various satellites. Excuse me. These are free space optics, so lasers between satellites, and no dolphins are involved, just the lasers. And no, it's not intended to kill the satellites. This is just for communication. So the inter-satellite links are not necessarily rock solid stable. Free space optics is a little bit tricky. As you imagine, you're taking a laser, you're pointing it at another object that is also moving, that is several hundred miles away, and you're trying to get them to communicate. And you want that link to stay stable, and there's mechanical things involved keeping the laser on target, heating, cooling, moving, things like the sun going behind your target can occlude the optics. So you get all sorts of problems going on. Couple this with, you've got a scale problem, you've got user stations. This is typically used as an access mechanism. So we want to scale to having millions of user stations that we're trying to talk to. So this gets interesting from a scale perspective instantly. So we have to deal with scale. We've got links that are changing frequently. We know that the uplinks and downlinks are going to be continually changing. We know the inter-satellite links are going to be very flaky. We're going to have to do traffic engineering. This is probably one of the things that's not obvious to folks who haven't been doing networking for a while. We are going to be bandwidth limited here. There's no question about that. It's widely expected that the uplink from the gateway to the satellite network is going to congest. This is because users tend to download more than they upload, and we expect that we're going to be bandwidth limited right there. Now, the inter-satellite links, I've heard various numbers. Some of them are optimistic, some of them seem pessimistic, but those are also going to be bandwidth limited. And so we're going to have to do some form of bandwidth engineering so that we can get bandwidth moved away from congestion and maximize all of our utilization of the bandwidth that we do have. So we do have to think about TE. Now, when we address scale problems, we only ever have one solution for scale, and that's to create hierarchy. We've never seen any other way. And the good news is that our link state IGPs already have a two-level hierarchy. And hierarchy is wonderful because it also helps us contain link change churn. And we're going to have a lot of that because of the ISLs. So we definitely want to think about a hierarchical solution. Now, hierarchy in OSPF is a little bit constrained. The way OSPF is defined, you have a backbone area, area 0, and all of your areas are tangent to area 0. And the question with this particular problem is that we don't have a good place to put area 0. We don't have a traditional backbone. We just have this swarm of satellites, and they're all circulating. There's no central location. There's no central high bandwidth portion. This just doesn't seem like a good fit. There are other people who have argued about this, but I still haven't heard a convincing argument on how this could be made to work. Hierarchy in ISIS is also two levels, but it is slightly different. Areas start at level 1, and then level 2 can be a connected subset of all areas. And this is different because we now no longer have to have a centralized backbone. And in particular, one of the things that we're going to do here is to take and put everything, the entire network, into level 2. Those of you familiar with ISIS are now screaming that this will not work and not scale, and you're absolutely right, except I've got a way. Stay tuned. One of the important problems also to solve is that of area partition. If you have enough links disconnect in the middle of an area, then your routing falls apart within that L1 area. And this is a long-standing problem. People have tried to propose lots of things, and they always come back to, well, let's build a tunnel from one side of L1 up through L2 and down to the other side of L1. And, well, tunneling is never a great way of solving connectivity problems. You add to your overhead and you're redirecting all of your traffic, and TE gets in the way, and it's just a mess. There is no good solution. The conventional wisdom is build your areas so that they don't ever partition. We don't have a better answer than that, even with ISLs. So one of the things that we want to do is to think about how can we build areas in a satellite network that never ever partition. And this is the question. So the proposal for how to solve this is something that I'm calling a stripe. We're going to take adjacent orbits of satellites. And the thing to remember here is that we've got multiple orbits going on. There are multiple satellites in each orbit. And they typically are separated by a few degrees of arc. They can see each other, and for the moment, we are going to expect that there are ISLs between the satellites in the same orbit helping link things together. And that should be a relatively stable ring. Now, these various different orbits are adjacent but I've drawn them. I don't have the PowerPoint skills to draw them in the correct way. They actually intersect at several points and diverge at several points. So they're not actually parallel to one another. They're actually at different angles. But logically, what we end up with is a topology where we could have ISLs between adjacent orbits. And we know that the ISLs between adjacent orbits are less stable than the ones on the same orbit. So then the question becomes, okay, if we have enough of these different orbits bound together, can we form an area that is known to be connected and reasonably stable from a connectivity point of view? The assumption here is that there is such a small number of orbits that we can form together into a stable area. And we call that a stripe.
Tony?
Yeah.
Is there statistically minimum number of link required to draw such a conclusion that you are always be connected?
That very much depends on the statistics about the ISLs, and I don't have any reliable statistics on ISL reliability. So this is where feedback from satellite operators would be very, very helpful. Is this a valid assumption? And we don't know.
I think practically, and our listeners are familiar with min links on logs, you like to have some logic where you say when number of active links is below threshold, I shut down whole thing. Probably you would need similar logic here.
Hopefully, but we don't ever want to shut down everything. So really what we'd like to do is just have this be a design time issue. If we have, say, 99% reliability of our ISLs, then this is probably not an issue. If we've only got 30% reliability of ISLs, then this is definitely going to be problematic. And we'd have to look and see, the number of ISLs on a given satellite is fixed. There's physical things involved. That's not going to change. So, if we've got very flaky ISLs, we may have real serious problems. And maybe this doesn't work. We don't know yet. So anyhow, once we have the concept of a stripe, then this topology becomes pretty simple. We take our adjacent orbits, we've got stripes, and then we wrap the entire planet in a bunch of stripes. And I've only shown 6 of them here, but that's PowerPoint limitation. Imagine there's going to be hundreds of them. Now, how do we make that scale? Now, one of the things in our toolbox is a proposal called Area Proxy. And this is an extension to ISIS. And the basic idea of this extension is to take an entire ISIS level 1 area, and we're going to abstract it out as a single node at level 2. Okay, this is radically different than what vanilla ISIS does, but it has some advantages. In particular, it means that we can capture a lot of the level 2 information and hide it. And that abstraction is very, very useful in this particular instance because we end up with one LSP per area, and that LSP just shows the links to adjacent areas. Okay, if we were using legacy ISIS, then every node would end up being present in L2, and that would be a scalability disaster. If we had a 40,000 node satellite network, conventional ISIS level 2 would be 40,000 LSPs. Okay, that's
if you would have kept it stable, you can still make it work. Churn is going to make it really disastrous, right?
Yeah.
Even 40,000, I think, would be give things indigestion. 40,000 plus churn is unthinkable. Okay, no, that's a non-starter.
Mm-hmm.
Okay, if we have area proxy helping us, then we reduce to one LSP per area, and now we're talking hundreds of LSPs, not even thousands. So that's well within what we can do. So now our level 2 topology looks very straightforward. We end up with just areas talking to other areas. And 6, but I've shown 6, but think hundreds here. And it's probably just a simple cycle. If we've actually got better connectivity than what I've shown here, then it's not much more complex graph than this. Okay. Okay, again, we have to do traffic engineering. We don't have infinite bandwidth. We've got limited capacity. We have a gateway that's going to act very much as a hotspot within its region. So we very much want to control traffic coming out of the gateway and coming into the gateway. Now, because all of the traffic from a region is flowing through that gateway, means that it has very, very good knowledge about what the traffic demand is. So all we need to do is to have the gateway decide where traffic should flow, and we can have it do the traffic engineering to control both inbound and outbound traffic. So then we just need a mechanism for directing traffic at the data plane. And for this, segment routing actually seems most appropriate. Okay.
And I think to add to that, a lot of people think of traffic engineering as bandwidth. Well-designed PCE system could take any constraint from time of the day to quality of laser to anything and make it part of constraint SPF computation. So you just prune part of network that don't meet the constraint. And again, could be pretty much anything. And you can inject a lot of proprietary satellite data into this to make right decision from traffic engineering perspective.
Absolutely. And in this case, the PC can be co-located with the gateway. It can be part of the gateway effectively. So you've got all of your solution right there. You can replicate things within the gateway, so that can still be reliable. So it's really straightforward. Most conventional traffic engineering done today is done with RSVP. We don't need that here. We don't need to have any kind of explicit setup. So that is just out of the way. All we need is a forwarding plane.
Tony, there's a question on chat if there's an area proxy implementation anywhere, ideally in open source.
I have not seen, I do know of one production area proxy implementation, and I cannot tell you if there are any others. So I certainly don't know of an open source one. The draft is out there, And I will happily tell you that I am one of the people who helped implement area proxy. So I can tell you that it is implementable and it does work.
So practically, if person who's asking if you're capable of writing code, there's reasonably stable implementation of ISS in FRR. Actually, it's been improved as speak because people want to use it at scale. There's probably one used by MikroTik. They just brought it out in 3-4 months. So just write it and draft it stable. It's in very advanced stage in ATF. And as Tony said, it has been implemented and it's actually working.
Cool. So for traffic engineering to work, the gateway is fulfilling the same role as PCE, so it needs full information for the topology. And in particular, it's going to have a number of stripes that it's going to use to reach its region. It probably doesn't need to know about all stripes in the entire topology. Okay, orbits, well, I don't know enough about satellites, but orbits don't change that radically at very high speed. So there's only going to be a few stripes that are going to affect a particular region. So to get that topology information, we're suggesting that the gateway get that from ISIS, and it can do that in a multitude of ways. It can participate in level 1 ISIS directly. If it's talking to multiple stripes, it can get all of it that way. You can also get ISIS information over a tunnel. That's a very common and straightforward thing to do. Or you can just get the topology via BGP-LS, and that's basically tunneling all of the same information over a TCP connection, again, back to the gateway. The gateway would then monitor traffic to and from each user station. That gives it a very good idea what the demand is on each user station. And then it can compute doing all the path computation per user station. And that allows us to optimize our capacity and avoid congestion. This is nothing fancy. This is very common, similar to what we would do in a terrestrial network. So no rocket science involved here.
Traditionally, we would distribute bandwidth over IGP. There are also pretty large solutions I'm aware of where PCE is combined with NetFlow collector. So you're actually reacting on real data, plain data, in order to change the metrics and implement traffic engineering.
Right. We don't have to do that here because the gateway already has all of the data directly available because it's the one doing all of the data forwarding into and out of the satellite network. So that's pretty straightforward. We can avoid a whole lot of net flow and traffic characterization and communication. So this is actually simpler. So again, we're proposing doing things with segment routing. And this is very convenient because it allows us to generate segment routing paths to do explicit paths for us. One of the things that was introduced in area proxy is also the concept of an area SID. And this is a MPLS label that would identify a particular stripe that we would be working with. And so now this can give us a SR path that's a MPLS label stack that contains areas, nodes, or adjacency SIDs, giving us a specific link that we want to use. And so the traffic engineering solution is going to present a label stack that's pretty straightforward. Okay.
It also allows for further compression. If you use binding SID, you could have not SID, link SID, or anything that more specific than that, expandable on the AnchorNet. So
Absolutely.
you will solve MSD problems here.
If you run into MSD problems, label stack depth problems, then yes, you could actually use binding SIDs. That's extra credit. Yeah.
There's a question: do you consider SRv6 as data control plane?
I did not go into SRv6. SRv6 does not apply to IPv4 traffic, and people still want to ship IPv4. SRv6 is actually going to, even with SID compression, is going to be bigger than what a label stack is probably going to look like for this application. As you'll see, we don't need a whole lot of labels. And microsids, they compress, but you're still using /120, 128 bits in the minimum case. A lot of cases, we're going to get below that. So let's talk about the various cases. Let's start with the simplest case. Let's say a gateway is sending traffic to a user station that's on the same stripe where the traffic is injected. Well, then we only need one label. We're going to need to forward the traffic to the satellite that is connected to the user station. And we're going to use the node SID for that satellite. And then we've got a raw IP packet underneath it. Okay. And once we've got that, okay, we're only adding one label. So this is a really straightforward case. The satellite strips its node SID and then forwards based on an IP destination address. Off-stripe forwarding is not harder. Okay. We're going to add an area SID. So we've got an area label and then a satellite and then the IP packet. So we've added 64 bits. The return case is pretty straightforward too. If we're doing a return on stripe, then we're going to have a node SID for the gateway. We just put that label on there, and then our IP packet is there. We're done. Off-stripe return forwarding, well, it's pretty straightforward again. We just need to specify the stripe and then the gateway, and we're good. 2 labels, that's all we need. Obviously, you can add more labels to do TE, but unless you're going to have a very complex path, this is going to be very small. That's about all there is to it. The good news is that IP addressing becomes very, very simple. The satellites only use IP addressing for reaching the next hop. Okay, so they never need to know about prefixes other than the ones that are immediately connected. You've got one prefix that's injected by the gateway into the internet, and all the user stations are numbered from that. Our addressing is now very well aligned to our topology. The satellites are completely abstracted away from the actual topology, internet addressing topology. So we're not violating Vector's law. Okay. We're basically finessing things. So this gives us a scalable solution for routing LEO satellites. It's relatively easy to extend this for mid-range or geosynchronous satellites as well. That's pretty straightforward. Using off-the-shelf production software, it scales to very large networks. It's gotten very nice low overhead in the forwarding plane, supports both IPv4 and v6, and gives us full traffic engineering functionality. Thank you very much, guys. Any questions?
I'll ask one question. So you probably know when satellites are deployed, they are not deployed evenly across the globe. They're actually parts of the world where there are literally no satellite connectivity over, right? Because of governmental issues, many things. So you will get incomplete connectivity graph. How do you see this working in such a situation?
It doesn't change anything. This routing architecture provides functionality where there is coverage. Okay, it cannot change the politics. It cannot change the fact that there are no satellites overhead. The point is to make things forward traffic when there is connectivity.
So let me rephrase the question. Probably, yeah. So there's different degrees of sparsity or density of connectivity. So at some point, you need to decide who you connect to, and whether you should be allowed to be transited and this kind of stuff.
Again, I'm trying to solve the simple case where this is an access network. I'm not trying to get into dealing with transit. You can do transit via satellite, and even with traffic engineering, but you need to play some games. So there's some small discussion of that in the draft, but didn't get into that because it didn't seem like there's a whole lot of need. And that seems like low order usage. Access still seems to be the primary usage.
There's a question. Can we bring it in so Tony can read it, or I can just read it? For sake of time, it seems you assume that all flows from a given user station will transit the same gateway. Is that true?
Yes, I'm making that assumption. If you want to run your network differently, you can. That seems like it would make things very complex, and that's making things complex leads to failures. So it seems like that's to be avoided.
Jeff, any questions on your side?
No, I was actually thinking of one of the statements you made early on about access to any one satellite may be as fast as just 15 seconds. Which anybody that's gone out in their backyard and watched the ISS go by certainly understands that idea, that nothing is in line of sight in low Earth orbit very long. Is that, as far as the handoff from one satellite to another, in that time, is that not pretty much the same as what you would get in a cell network, other than going the other way around? The antenna is moving rather than the mobile device is moving. And would you have the same kinds of handoff challenges going from one station to another?
Absolutely. You're going to have exactly the same kind of issues. And thankfully, in the cell network, the link layer handles that. IP routing does not. And so I'm expecting very much that the satellite network is going to have some handoff protocols that are going on. What it looks like is completely proprietary, so I leave that solution to them.
Okay, thank you.
So, but the assumption that you almost never completely lose reachability, right? You lose some part. You get reduced bandwidth, not lack of reachability.
Right. If a user station can't see any satellites, obviously there's nothing that I can do to fix it, right? And it's just going to be that way. Most of the time, from reports that I've heard of people that do have satellite connectivity, they do have some outages, but they're relatively rare and they're reasonably smooth. The rest of the time, things are very solid. So, the handoff problem is actually apparently well solved.
Cool. That's all the questions I can think of.
Cool. Thank you, guys.
Yeah, so from my side, I can only say, the draft caught my eye because of its beauty and simplicity. It's simple, it's implementable, and this is what we are looking for in, internet space, ATF space. No one wants to see something that's academic, non-implementable, and just done for sake of paper. Mm-hmm. Thank you, Tony.
Thank you, Tony. Appreciate you taking the time to join us. Bye, everybody.
Bye, everybody. Bye, Tony.
Bye, guys. Thank you.
Thank you.